So for item number 3, we're finding the dimensions of the largest isosceles triangle that can be inscribed in a circle of radius 4 centimeters. So from that information, I determined that we want to maximize the dimensions of the isosceles triangle, which would, in the end, maximize the area of the triangle. So we want to maximize the equation a equals 1/2 times 2x y, and then in parentheses y plus 4. So I got this equation because area of a triangle would be 1/2 base times height. And so when I made this diagram, so you have the circle and then an isosceles triangle. So I made the isosceles triangle within the circle, and you know that the radius is 4, so from the middle to the top of the triangle would be 4, and then from the middle to a corner, a vertice of the triangle would be 4 as well. So then we know that this would be a right triangle because we can drop the altitude and it would be a right triangle. So I labeled these both x, and then I labeled this y. So y plus 4 is our height and 2x is our base. So in order to maximize the area, we have to first get a in terms of one of the variables, so either x or y. We do this by using the fact that the radius with the altitude creates a right triangle with sides x and y and hypotenuse 4, like I mentioned before. So then we're able to say 4 squared equals x squared plus y squared, and we can solve for x, or you can solve for y. Either you prefer. I chose to solve for x. So x is equal to radical 16 minus y squared, and then we're able to substitute this into the area formula and simplify that. So the area formula would be radical 16 minus y squared times parentheses y plus 4. So then we're able to take the derivative with respect to y. I think I had written that because we were talking about if you decided to take the derivative with or solve for x or solve for y instead, then you'd want to take it with respect to x. So yeah, we took the derivative and then we're able to set the derivative equal to 0 to then solve for the critical points in order to find the max and min values. So we solved that and got y equals 2, and then y equals -4, and then y equals 4 is also a critical point because in the original equation, when we set it equal to 0, you can't have 0 in the denominator, so 4 would make this 0. So we got 2, -4, and +4. So we're using the critical points that we found in the endpoints of the domain. We want to plug it into the original area equation to see which x value maximizes the dimensions of the triangle. So we found that plugging in 4 and -4 just gives you 0, and so when you plug in 2, it'd be 12 radical 3. Another way of looking at this is we can also see that 2 is a maximum if we look at the graph of the area equation. So I just put this into Desmos and said area is equal to radical 16 minus y squared, and then y plus, I think I changed it to x so Desmos understood. But yeah, so you can see that 2 would give you your maximum, being a maximum. And so from the solutions above, we determined that y equals 2 would maximize the area of the triangle. So then we can solve for x, which would be 2 radical 3, and then thus the dimensions of the triangle would be a base of 4 radical 3 and a height of 6. So that is the conclusion that we came to.